Hey there. Hope all is going well. We are moving on from chapter 8, the one sample Z statistic, doing hypothesis testing, and moving on to the first of several T statistics that we're going to learn. And so this is a lecture typically when I'm teaching this in an in-person class. We typically spend 2 lecture periods on, so that's what we're going to do for this chapter here in the online environment as well. And it may seem like things are moving a bit slow because we just spent 3 lecture periods on the previous chapter. But this is important foundational stuff for you to learn. Remember, our goal here is for you to learn how to do statistics and to prepare yourself for success in the rest of the major and beyond, right? This is not a race. So, certain chapters we're going to slow it down a little bit and take our time, give you a chance to read the chapter thoroughly, give you a chance to watch portions of these lectures over a period of 2 or 3 days, because we don't necessarily need to rush things. Remember, we've got an entire semester to do this class, and there is a method to our madness, if you will. One thing that you'll notice starting in this chapter and the remaining chapters on t-test, right? So chapters 9, 10, and 11. Each chapter includes some information on something that we call confidence intervals. And remember, I'm going to lecture about confidence intervals in 1 lecture, right? And we're going to do that after you've learned the 3 basic t-tests. So I'm just going to teach you how to do the t-tests for a 1 sample, an independent sample, and a related samples t-test. And then after we're through that, I'm going to lecture about the different confidence interval equations that you would have read about in chapters 9 through 11. So if you're wondering when that date is going to be, just see the syllabus, right? That'll tell you exactly which date I'm going to do that lecture. And I will remind you in the lecture previous to that class what's going to happen so that you can go back and reread these little sections in each of these 3 chapters on the confidence intervals, so you'll be very well prepared. Okay, so what have we done so far? Well, we've done a 1 sample Z-test, right? And we've learned the 6 steps of hypothesis testing, right? Stating our null and our alternative hypothesis, using the unit normal table to find our critical value. We've collected some hypothetical data and run a test statistic, in this case the 1 sample Z. We've compared the results of that test statistic to that critical value that we looked up in step 2 and made a decision as to whether or not we reject or fail to reject the null. If we reject the null hypothesis, then we learn how to conduct a effect size test, right? We've learned how to do the Cohen's d. And then we've written up our results in APA format as required by the sort of rules of the major, right? Following our APA standards. Okay, fantastic. Now, there's a problem with the 1 sample Z-test, right? Sort of a real-world obstacle. The population standard deviation is required in order to compute the standard error of the mean, right? The thing is, typically, we don't necessarily know what the population standard deviation is, right? That's this little lowercase sigma there, right? So what is it that we do when we don't know the population standard deviation? Well, let's start out our story with a story about beer. I don't know, maybe you don't like Guinness beer. If you do or you don't, I guess it really doesn't matter. You should know, though, Guinness is the company to blame for the set of statistics that we're going to learn over the next several chapters. The student's t-test takes its name from William Seeley Gossett's 1908 paper. It was published in a journal called Biometrica, and it was published under the pseudonym Student. So Gossett worked at the Guinness Brewery in Dublin, Ireland, right? And his job involves sort of a quality control in terms of things like the barley, yeast, hops, right? All the ingredients that are used to make the beer. So given the size of the Guinness Brewery, there were huge amounts of these ingredients. And it would have been economically very expensive and in some cases, most likely impossible to test the entire population of all these different ingredients at the brewery. So Gossett needed to solve a problem, right? He needed a method for making conclusions about huge quantities of ingredients from very small sample sizes, right? And he needed to do this without knowing the population's standard deviation, right? He couldn't know the standard deviation for all the different amounts of barley and yeast and hops and things like that that they had at the brewery. So today we call this statistical test that he developed the student's t-test, or more simply just the t-test. And sort of one version of the origin of the pseudonym is that Gossett's employer preferred staff to use sort of anonymous pen names when they were publishing scientific papers instead of their real name. So he used the name student to hide his identity. And another version of the sort of story is that Guinness just didn't want their competitors to know that they were using the t-test to determine sort of the quality of all their raw materials. But anyway, he developed this test as a means of comparing samples when the population standard deviation is unknown, right? Okay. Like I said before, many of the steps from here on out, really all the way to the end of the semester, should be very familiar, right? So for a one sample t-test, we're going to perform the same 6 steps for hypothesis testing as we did for the z-test, right? But now we're going to be dealing with a t-statistic and a t-distribution instead. So some of the things that we do that we learned in the z-statistic are going to be a little bit different. Like, for example, one of the things that's going to be different is how we determine the decision criteria. So now we're going to find a t-critical in a new table, right? We're not going to be using the unit normal table that we use for the z-statistic. We're going to be using a different table. But we're still going to be doing, comparing the value of that t-critical value that we look up. We're going to compare that to the t-statistic that we compute. So in step 4, we're still going to make a decision about whether we fail to reject or fail to reject the null, or whether we reject the null. We'll still compute an effect size, but a few things here and there are going to change. Like, for example, in step 6, the way we state our results in APA format are going to be a little bit different. All right. So again, here's this is an important sort of thing that I want to really get you guys to make sure that you memorize, right? If you know the population standard deviation, right, and you're comparing a sample mean to some sort of hypothesized population means, some value that's out there that sort of we didn't collect, right, that we're comparing our sample data to. If that's the case, right, if you know the population standard deviation, then you would run a one sample z-test, right? But as is often the case, if you don't know the population standard deviation and you're comparing a sample mean to some hypothesized population mean, then you would use a one sample t-test, right? You'd run a one sample t. You commit this idea to memory, right? Your notes, whatever, right? You're often going to be presented scenarios in the homework, in the exams, the quizzes, where you're going to need to read a description of an experimental scenario, and you're going to have to figure out which type of statistical test that you need to use. All right. Now, here are the equations for a one sample t-test, right? And the logic is the same as what we've been doing before, right? We've got this idea of an obtained difference. Here we're going to take our sample mean minus our hypothesized population mean, and we're going to divide that by some difference we expect by chance, right? Some sort of error term. And here we're now going to, for a one sample t, for a one sample z statistic, we call the denominator of our test statistic the standard error of the mean. Here, for a one sample t, we're going to start calling that the estimated standard error of the mean. The estimated standard error of the mean. And here's the equation for that, right? And it shouldn't be too terribly complicated to wrap your head around because we don't have the population standard deviation. We're going to be using the sample standard deviation as a stand-in, right? As a stand-in for the population standard deviation, right? And all of this is fine, right? It works quite well as long as you have an appropriate sample size, right? So sort of think about the rules of the central limit theorem, right? The larger the sample size, right, the more our sample mean starts to approximate our population mean, right? We know this because of the law of large numbers, right? We also know that with a large enough sample size, we're going to reduce our variability, right? Our overall variability should decrease if our sample size is appropriate. So this means with an appropriate sample size, using the sample standard deviation as an estimation of our population standard deviation, it's going to provide an overall good estimate, right? And so we can treat our t very similar to how we treat our z-score, right? It's sort of as a warning, typically if we have a small sample size, then t is going to be a very poor estimation of z. But again, as long as our sample size is appropriate, then it's okay to use the sample standard deviation as an approximation, if you will, for the population standard deviation. Because if our sample size is large enough, then all the aspects about our sample size, right, the mean, the variability, they should all be a reasonably decent approximation for the respective population parameters. All right. With z-scores, we had just one distribution that we were dealing with, right? That was the unit normal distribution. And that was fine because we were working with sampling distributions that we knew to be normal. Now that we're only using sample data, right, a sample mean and a sample standard deviation, we don't necessarily know that our sample distribution is going to be perfectly normal, right? Again, if our sample size is large enough, it should be normal-ish. But the thing is, our distribution when we're just dealing with the sample really could be any shape, right? In fact, the t-distribution itself can be thought of as a family of curves. And there is one curve for every possible sample size that we have. Now, I don't want you to worry too much. I don't want this to be too complicated of an idea or too abstract, right? Remember that the law of large numbers, the central limit theorem, it suggests that if our sample size is large enough, then our sample data should be normal-ish, right? And so what I want you to continue to do on the homework is sketch something that looks like a normal curve, label where your critical regions are. Once you've computed your test statistic, I want you to go ahead and plot where that is on the curve. Do the same things that you were doing with a one sample z statistic. Because again, even though a t-distribution isn't a perfectly symmetrical distribution, it's still something that should be normal-ish if our sample size is large enough. And the greater our sample size, the more normal that distribution is going to look. All right. So again, just continue to sketch something that looks like a normal curve, label the mean, label your critical region, you plot where your actual score is, and everything will be fine. But this is just something you need to sort of conceptually wrap your head around, this idea that there's a different curve for every t-distribution that varies based on our sample size. It varies based on really our degrees of freedom. Okay. So let's go through the 6 steps of hypothesis testing. Step 1 is stating the hypotheses. And here's some good news. It works exactly the same way we learn how to do it for the one sample z-test. And why is this the case? Well, it's because we're still comparing one sample mean, right, that we've collected, right? We're pretending we've collected that data. We're still comparing that sample mean to some sort of hypothetical population mean, right? So the way we state our hypotheses doesn't change. So we're still going to be talking about our sample mean in relation to some sort of hypothetical population mean. So we're still going to be looking at the word problem, identifying whether or not it's a 1 or a 2 sample test. If it's a 2 sample test, we're going to have two tails, right, in our distribution. If it's a one tail test, we're going to have the entirety of our alpha either in the left side or the right side of the distribution, right? Just like we did with the z-test. One thing, though, we won't have to do, if it's a 2-tailed test, we're not going to have to divide our alpha in 2 like we did in the 1 sample z. But I'll talk about that when we get to step 2, which we're at now, right? So finding the critical values and the probability. Sorry, I had to have something to drink. All right. So in order to find our T critical value for step 2, there's a few things that we need to know. One thing is, again, is it a 1 or 2-tailed test? What is our alpha? And what is our degrees of freedom, right? So remember, we used the degrees of freedom to calculate our sample variance, right, which led to our standard deviation. So now that we're working with sample standard deviation, we're going to continue to use degrees of freedom now when we look up these values in our table. So the degrees of freedom formula is just like we learned in chapter 4, right? It's sample size minus 1, so n minus 1. So we're also going to be using a different table to look up our critical value, right? So before we used the unit normal table, now we're going to use the T table, right? That's table B2, right? You should be able to find that on page 651 of the current edition of the textbook. And in many respects, it's similar, right? You're going to need to find a column and you're going to need to find a row, and where those intersect, that's going to be our T critical value. So your alpha and your tail are going to tell you what column to look in, and your degrees of freedom are going to tell you what row to look in. All right. So a couple of things here to keep in mind. Like I said, you're no longer going to have to divide your alpha in 2, right? Let's say your alpha was 0.05 and you're looking for a 1-tailed test. Well, you'd find the row in your book that shows the proportion in 1 tail, and you'd find the alpha of 0.05, and this would be the column that ultimately you'll find your T critical value. But let's say you had a 2-tailed test. Well, fortunately for us, it already just sort of does that division problem. So what we would do is we would look in the row for proportion and 2 tails combined. We'd find that alpha of 0.05, and this would be the column that we look up to find our T critical value. And then in order to find the actual row that we'd be using, you would locate your degrees of freedom in this far left column over here. And once you find it, well, you just go all the way over across to whatever column, right? This would be proportion in 1 tail, and this would be proportion in 2 tails combined. And that's going to give you your T critical value, right? So first you need to know, is this a 1 or a 2-tailed test? Then you need to know your alpha. Again, typically the convention is 0.05, but it might be different in some of the problems that we do. And then you're going to need to know your degrees of freedom, and that's how you can find the critical value. Now, my table here, it's a little bit different than what you have in the book, but you should be able to follow along. Let's say we had a sample size of 41. Our alpha was set at 0.05, and it was a 2-tailed test. What would be our T critical value for this scenario? Go ahead and pause the video, figure that out. Might be easier for you to see in your textbook, and then when you come back to the video, I'll show you how I got that answer. All right, so with a sample size of 41, our degrees of freedom are going to be 40, right? So the degrees of freedom formula is n minus 1. So that's going to give us the degrees of freedom of 40. We know that this is a 2-tailed test, so we're going to use the 2-tail row. We know our alpha is 0.05, so we're going to locate 0.05 in 2 tails. And when we go down that column all the way to the degrees of freedom 40, right, we get a T critical value of 2.021. We would just round that to 2.02. What if our what if our N was 121? So we have a very large sample size. Our alpha is 0.05 and it's a two-tailed test. Go ahead and pause the video and see if you can figure out the answer. I'll give you the answer when you come back. Okay, so this can get kind of tricky. Sometimes you'll notice that unfortunately, I think my little example that I found on the internet and your table might be a little bit different, but the logic here is still the same. You're going to run into scenarios where your degrees of freedom isn't in your table, right? So for example, in my version of the table, it goes all the way to 30, but then it jumps to 40, then it jumps to 60, 80, 100, and so on. And the actual degrees of freedom for this scenario would be 120. It just happens to be the case that I don't have a degrees of freedom for 120 in my table. So when that's the case, you want to use the more conservative value. So you want to use the next lowest degrees of freedom. In this case, you always round down to the lowest value. You don't round up to the highest value, right? So in this case, the next most conservative degrees of freedom is 100. I'm still looking at 0.05 and two tails. So in this case, the correct T critical value would be 1.984. Which would round out to two decimal places to 1.98, right? So we're always going to use the most conservative degrees of freedom to find our critical value. Now, I want to point out, this doesn't change your actual degrees of freedom, right? If we were writing up our results in APA format, we would still say that our degrees of freedom is 120. It's just we don't have a degrees of freedom of 120 in our table. So I'm going to choose to use the convention here is using the next most conservative value. So in that case, I'd use the degrees of freedom of 100, and I'd find the T critical that corresponds to that particular degrees of freedom. But it doesn't change the fact that my degrees of freedom are going to be N minus 1. So 121 minus 1 is going to give us a value of 120. All right, what if my sample size was 10? I had an alpha at 0.01 in a one-tailed design. Pause the video, see if you can figure it out, and I'll give you the answer when you come back. Right, so our degrees of freedom is going to be 10 minus 1, so it's going to be 9. We're looking in the one-tail row for an alpha of 0.01. So when we go down to a degrees of freedom of 9, we find a T critical value of 2.82. And remember, like I said, T is really an estimation of Z, right? So the larger my sample size, the closer my T statistic is going to approximate my Z statistic. So this is just a conceptual idea. Imagine what would happen if our degrees of freedom started to approach this idea of infinity. Well, if that really happened, of course it can't happen in the real world, but if it really happened, note that our T critical values would actually be the same thing as our Z critical values at a 0.05 in one tail or a 0.05 in two tail. And you might remember, right from the previous chapter, a Z critical value of 0.05 in one tail turned out to be 1.64, and the Z critical value for 0.05 and two tails turned out to be 1.96, right? So again, as our sample size increases, our sample starts to approximate a more normal distribution. It starts to approximate our population parameters, and T becomes a better estimation of our Z statistic. All right. I mean, again, this doesn't happen in reality, but it's just sort of reinforcing this idea that, look, we're using a sample in every way, shape, and form as a approximation of our population data. And it works best when sample sizes are appropriate. Okay. So let's say we rejected the null hypothesis in step 4. It would be appropriate to compute an effect size. And we can still do that in a T statistic, except the only thing that's different is instead of using our population standard deviation in the denominator of our Cohen's d, we're going to go ahead and use our sample standard deviation as a stand-in there, right? So we take the sample mean minus the population mean, and whatever that is, we're going to divide that by our sample standard deviation. And our interpretation is the same, right? We're going to interpret that using that little table that we used before in the past that you can find in slides for chapter 8. And we're still going to report it out to 2 decimal places. And if it's a negative value, we're going to compute the absolute value of Cohen's d, right? So essentially, we're just going to treat it as a positive value, report it out to 2 decimal places. If it's anything, if our Cohen's d is anything less than 0.2, we'd say that's a small effect. Between 0.2 and 0.7, 0.8-ish, we'd say that's a medium effect. Anything above that, we'd say is a large effect. All right. So again, here are the 6 steps to hypothesis testing. Again, we're going to state our hypotheses the same way as we did with the one sample Z statistic. We have a much different experience, right? Different things that we have to do when we're looking up the T critical value, right? We're using a different table. We don't have to divide our alpha in 2 if it's a 2-tailed test. And we need to find our degrees of freedom in order to find the row, ultimately, that we're going to link up to our correct column based on whether it's a 1 or a 2-tailed test and whatever the alpha is. And that'll give us our T critical value. Obviously, some new ways that we're going to compute the test statistic, namely using our sample standard deviation instead of our population standard deviation to compute the estimated standard error of the mean. Our criteria for making a decision doesn't change. The only thing that changes about our effect size, again, we'll compute the effect size only if we reject the null hypothesis. And instead of using the population standard deviation in the denominator of our Cohen's d, which we don't have, we're going to use the sample standard deviation to compute the effect size. And again, we're still going to report our results in APA format. And it's a little bit different now with the T, not much different. And when we actually get to some practice problems, I'll be a lot more specific in terms of how we report our statistics. Okay? All right. So let's go ahead and do an example now, right? So I want you to run a one sample T statistic. I want you to do all 6 steps of hypothesis testing on this scenario here. And here's the scenario. The company claims that there are 16 ounces of cereal in each box of cereal that they produce. And I claim that that's not the case. I think there's actually less cereal than 16 ounces in your typical cereal box, right? And what I want to ask is there a significant difference, right? Is there significantly less cereal in my sample compared to my population mean? And I'm going to test this at an alpha of 0.01 for some silly reason, but we'll go ahead and, since that's what I have on there, we'll do it. So imagine I've collected this sample data, right? So I went out to the store, I bought 10 boxes of cereal from some cereal manufacturer, and I emptied each box into a scale, weighed each box one at a time, and I computed the mean weight of these 10 boxes of cereal. It turned out to be 15.8 ounces. And I went ahead and computed the standard deviation for my sample of 10 cereal boxes, and that sample standard deviation turned out to be 0.45. So what I want you to do is pause the video and try and do all 6 steps of hypothesis testing. When you come back, I'll run through them and we'll see how well you did compared to my work. Okay, so go ahead and pause the video and give it a good shot. All right. The first thing we need to do is state the null and the alternative hypotheses. And like I said, the strategy that you want to employ here, first and foremost, is to determine whether or not you're dealing with a one-tail or a two-tail test. And I'll go back to that previous slide. It's a one-tail, right? Because I'm making a claim here that my sample, right, my 10 boxes of cereal that I weigh, that I test, should be less than the 16 ounces that the cereal manufacturer claims they put in each box, right? So when that's the case, remember, I think that the best strategy is to do the alternative hypothesis first, right? Because the alternative hypothesis really sort of states the prediction that you make as a researcher. So what I'm saying is the sample, the mean of my sample, right, in ounces should be less than 16, right? So my sample should be less than 16 ounces. That's the population parameter here, right? That's sort of essentially the population mean, since the cereal company says, well, we put 16 ounces in every box exactly. We can treat that 16 ounce figure as a sort of hypothetical population mean. So my sample should be less than my population mean. Whereas alternatively for my null, my sample should be greater than or equal to the population mean of 16 ounces, right? So this is essentially saying there should be no difference between my sample and the population, whereas the alternative is my sample should be less than the population mean of 16 ounces. Okay. Now we need to find the t-critical value, right? So again, we identified this as being a one-tailed test. Our alpha is 0.01, and we need our degrees of freedom as well in order to find our t-critical value. Our sample size was 10, so 10 minus 1 equals 9. So our degrees of freedom in this case are 9. So again, we're going to want to look in the row for the proportion in one tail, and we want to find an alpha of 0.01. So that's telling us to look in this column right here. Then we need to find our degrees of freedom, which is 9, right? So that's the row we're going to look. If we go all the way over to the 0.01 column, proportion in one tail, we find our critical value to be 2.82. And to be clear, this critical value should be negative 2.82, right? Let me jump back to my alternative hypothesis. I'm making a less than prediction here, a less than prediction. So that means that my critical value is going to be a negative value, and the entirety of my alpha, because it's a one-tailed test, is going to go in the left side of the distribution, right? It's going to go to the left of the mean, right? And again, this is an important idea, right? It's something that even if you can't sort of wrap your head around the sort of theory behind it here, just commit it to memory, right? If your operator for your alternative hypothesis in a one-tailed test is less than, that means your critical value that you look up in your table has to be a negative value, and that means the tail of your distribution is going to be on the left side of the distribution. If this symbol were a greater than sign, right? So if your operator in your alternative hypothesis is a greater than sign, well, that means your t-critical is going to be a positive value, and the entire tail, right, the entire alpha is going to be to the right of the mean, right? So it's going to be in the right side of the distribution. But here we have a less than prediction, right? My prediction is my sample mean will be less than my population mean, right? So that means our critical value is going to be a negative value, and it's going to fall in the left side of the distribution. So when we compute the test statistic, if it were to fall to the left of our critical value, in other words, if it's less than negative 2.82, then we would reject the null hypothesis. We would say that the amount of cereal in our sample, right, the mean amount of cereal in our sample is less than, significantly less than what the manufacturer claims. However, if it falls in this big region over here, right, if it's greater than negative 2.82, so any value more than negative 2.82, well, we would say that's not necessarily an unlikely observation under the assumption that the null hypothesis is correct. Therefore, in that case, we would fail to reject the null hypothesis, and we would say, yeah, there's no difference between our sample mean and our hypothetical population mean. So now we've got all that plotted, right? The thing we want to do now is simply compute our test statistic, right? And so the first thing we need to do is compute our estimated standard error of the mean, right? Our estimated standard error. And remember, we don't have our population standard deviation, so we're going to use our sample size as a stand-in for that. That's going to go in the numerator of our estimated standard error of the mean equation. And we're going to divide that by the square root of our sample size. So remember from the previous slide, right, our standard deviation for the sample was 0.45, and our sample size was 10, right? So we can plug those values into this estimated standard error of the mean equation, right? So 0.45 divided by the square root of 10. And that's going to give us a estimated standard error of the mean, which again, don't get thrown off here. A lot of times I'll just abbreviate this as SEM. It means the same thing. Our estimated standard error of the mean is 0.142. Now that we know that, we can compute the t-statistic, right? Because that 0.142 is going to go in the denominator of our test statistic. In the numerator, we're going to take our sample mean and subtract from that our hypothetical population mean. So we're going to take that 15.8, right? That's the average weight of the 10 cereal boxes in my sample. From that, we're going to subtract the hypothetical population mean of 16, right? Because the cereal company says they put 16 ounces in every box. And whatever that deviation is, we're going to divide that by our estimated standard error of the mean. And when we do that, we get a t-statistic of negative 1.41. Okay, great. So now we need to plot the results of our t-test into our distribution that we plotted out earlier, right? And so that's going to be somewhere around here, right? So the results of our t-statistic were negative 1.41. If we were to plot that in our distribution, this is where it falls. And so now we have to ask ourselves, well, does that fall within our critical region? And the answer to that question obviously is no, right? If it fell into our critical region, it would be somewhere over here. It would have to be less than negative 2.82. It happens to be that the computation turned out to be negative 1.41. So it does not fall within our critical region. Therefore, our decision here is to fail to reject the null. And what that means in the real world is that the sample mean of the weight of my 10 cereal boxes was not significantly different than the weight of cereal that the manufacturer claims to be in every box, right? So then the question is, we go to step 5, do we compute an effect size? Well, the answer to that question should be no, right? We only compute an effect size when we have significant results. That means that we only compute an effect size if we reject the null hypothesis. In this case, we failed to reject the null hypothesis. That means we have no effect, right? So there is no effect size to compute. It would be inappropriate to do that. And if we failed to reject the null hypothesis when we were doing our homework, and we went ahead and computed an effect size anyway, that would be a correct answer. The only correct answer in that scenario is NA, not applicable. So we would probably lose, I believe, a point, if I recall correctly, if we compute the effect size, yet we've failed to reject the null hypothesis. It would be wrong. And so now we want to write up our results in APA format. And just like before, when we learned how to do a one sample Z statistic, there were sort of 3 individual sort of parts to step 6, right? The first thing is we had to state whether or not we rejected the null or we failed to reject the null hypothesis. And in this case, for our serial example, we failed to reject the null hypothesis. So that's the first thing that we should say, followed with a comma. Now we want to report the results of our t-statistic. So we have a lowercase t, and in parentheses, we report our degrees of freedom, right? So remember, our sample size was 10. So our degrees of freedom, 10 minus 1 is 9, right? So t, and in parentheses, our degrees of freedom, equals the results of our t-statistic. That was negative 1.41. And then we want to say something about the alpha here, right? Well, our alpha was 0.01, and since we failed to reject the null hypothesis, we would report our p-value as p greater than 0.01, or we could say p equals ns, right? But you want to make sure that this little sign here is correct. It's going to be p greater than 0.01, not p less than 0.01. We would have said p less than 0.01 if we rejected the null hypothesis, but we failed to reject the null. So therefore, we want to say p greater than 0.01 or p equals ns, right? So all of this is sort of the second sub-step of step 6. And then finally, the final step of sub-step of step 6 is that we want to state our results and report things like means and standard deviations and all that other good stuff. So my write-up was pretty simple here. I just said the average amount of cereal in my sample, right? And then I want to report my sample mean and my sample standard deviation in parentheses, which is what I do, is not significantly different from what the manufacturer claims. And there I use my mu symbol, and I report the population mean of 16 ounces in this case. And that's all you got to do. That's it. That's all you need to do. So hopefully your effort was exactly like mine, right? Which would be a good sign. That means that you have a pretty good understanding of how to run a one sample t-statistic. So just to recap, right? If you're going through one of these scenarios, right, you ask yourself, well, do I know the population standard deviation? If you do, right, if you read through one of these word problems, if you know the population standard deviation, then you would run a one sample z-test. And that's what we learned how to do in chapter 8. But if you don't know the population standard deviation, you would run a one sample t-test. And that's what we're learning to do in this chapter, right? That's what we just did. Now, what if you have more than one sample, right? What if you collect the sample that experiences your control condition, and then you collect another sample that experiences your experimental condition? And in this case, you're not comparing these samples to some sort of hypothetical population mean, right? You're not comparing it to some sort of outside number, right? Some number that represents a population parameter. Well, in that case, you would run what we call an independent samples t-test. And that's something that we're going to learn in chapter 10, right? I'm not going to lecture about that today. I'm just sort of hinting, giving you sort of a foreshadowing of what to expect in the next chapter. Okay, let's do a little bit of practice here on some things, right? I'm going to put up a few practice slides here. I want you to see if you can figure out the answer. So here's an example, right? A researcher plans to test whether men differ from women in their ability to remember the names of food. So using a sample size of 31, right? So n equals 31 and an alpha of 0.05, what critical t value should be used, right? So I want you to see, use your book, right? Use your book, use the table in your book, and see if you can figure out the answer to this question, right? What's the t critical value or values? And then when pause the video, and when you come back, I'll show you how to do it. Okay, so you're going to need your table, right? And here's some things you need to know, right? You need to know your alpha, which is 0.05. Hopefully you identified that this is a two-tailed test, right? So if I flash back to it really quick, there's no directional prediction here, right? It just simply says, well, a researcher wants to test whether men and women are different. Right? It's not, there's nothing in this word problem here that says, oh, I predict, men will be worse or men will be better, at remembering the names of food or vice versa. It doesn't matter. There's no a priori prediction or directional prediction, about how men and women, should specifically differ, in terms of their ability to remember names of food. It's just asking, are they going to be different? Right? So that means it has to be a two-tailed test, right? When there's a lack of a directional prediction, that means our default here is that we think this is a two-tailed test. So we know the alpha is 0.05. We know it's a two-tailed test. We know the sample size is 31. So to figure out the degrees of freedom, right, we're going to go n minus 1, right? So 31 minus 1 is going to give us a degrees of freedom of 30 in this particular scenario, right? So when I take all that information, right, two-tailed test, alpha of 0.05, degrees of freedom 30, I see that the correct t-critical value in this case should be 2.042, or we would really round that to 2.04. Okay, let's try another one. This is a really good conceptual question, right? I feel like I've asked different versions of this before, and I may yet continue to ask different versions of this question as we learn more statistical tests, because I really want you to be able to wrap your head around sort of all the parameters that are in play that affect our interpretation of our results, right? So which combination of factors will increase the chances of rejecting the null hypothesis, right? Would it be A, a large standard error and an alpha that equals 0.05, B, a large standard error and an alpha that equals 0.01, C, a small standard error and an alpha of 0.05, or D, a small standard error and an alpha of 0.01. I want you to go ahead and pause the video, see if you can figure out, and I'll give you a hint. None of this requires any math. Like, you could make up some numbers if you wanted to, and you could sort of test this on your own. But here's the thing about this question. You don't have to do any mathematics in order to answer this question. And you've taken one of my exams. You know, there's going to be, you had a few questions like that on exam 1. You can expect some similar, a handful of similar questions on exam 2, right? Questions that just test your conceptual understanding of statistics, that don't require you to do any math. So pause the video, see if you can come up with an answer to this question, and then I'll give you the answer. Okay, so let's sort of break this up into parts here, right? Let's just focus on the first part here. Will a large or a small standard error increase the chances of rejecting the null hypothesis? Well, okay. Remember that the standard error, right, whether it's the actual standard error of the mean or the estimated standard error of the mean, this is the number, right? This is the value that's going to go in the denominator of our test statistic. It doesn't matter whether it's a one sample Z statistic. It doesn't matter whether it's a one sample T statistic. This is the value that's going to be in the denominator of our test statistic. So think about it this way. If I'm dividing some difference between my sample mean and my hypothetical population mean by a large number, am I going to have a large T statistic? Or if I'm dividing that by a small number, let me rephrase that. Actually, let's scratch that. Which one of these scenarios is more likely to produce a large T statistic, right? If I'm dividing the difference between my sample mean and my population mean by a large number or a small number? Well, hopefully, intuitively, you figure out, well, actually, if I'm dividing that difference by a small number, then I'm going to get a larger T statistic. If I'm going to get a larger T statistic, that's going to increase the chances of rejecting my null hypothesis, right? So we can already rule out A or B, right? Our answer has to be C or D. And let me demonstrate this idea here, right? So here's our serial example, right? And when we divided that by 0.142, right? When we divided the difference between our sample mean and our population mean by a standard error of the mean of 0.142, we got a test statistic of negative 1.41. And for our example here, we're going to pretend that that's a large estimated standard error of the mean. Let's do the same example, and let's just pretend, this doesn't have anything to do with the reality of our computation, but let's pretend that our estimated standard error of the mean was 0.07 instead of 0.142, right? So if we take the same difference between our sample mean and our hypothetical population mean, and we divide that by a much smaller standard error of the mean of 0.07, look what happens to our T statistic. We get a value of negative 2.86, right? So if our sample, or it doesn't matter whether it's our estimated standard error of the mean or actual standard error of the mean, if we're dividing the difference between our sample mean and our population mean by a small estimated standard error of the mean or regular standard error of the mean, we're much more likely to get a larger T statistic, and we're much more likely to reject the null hypothesis. What about alpha, right? What about alpha? Well, we could just look up this value in the table, right? We can look up, well, what would be our alpha two-tail test at 0.05, and what would be our alpha at a two-tail test at 0.01? So let's see what we got here. 0.05 in two tails combined, right? We get an alpha of 2.26, right? Okay. What about 0.01 in two tails combined? Oh, we get an alpha here. A critical value of 3.25, right? 3.25. So the larger, let me start again. The smaller our alpha, right? The more extreme our t-test at step 3 has to be in order to reject the null, right? If our alpha is set at 0.05, then we just need to get a value of something beyond 2.62, right? But if our alpha is set at 0.01, our t obtained statistic has to be greater than 3.25, right? So the answer is C, right? A small standard error and an alpha of 0.05 out of all of these options here is the one that's going to produce the more likely scenario of being able to reject the null hypothesis. Okay, let's do another one here. In the United States, 18 to 24-year-olds spend an average of 981 minutes talking on their cell phone each month. I suspect that BlackBerry owners spend less time than that. Which of these following sets of hypotheses is the correct null and alternative for that particular prediction? So go ahead and pause the video, and I'll give you the answer when you come back. So here it is, right? Remember, what we want to identify here is this a one or a two-tailed test? And clearly, it's a one-tailed test, right? Because I have a prediction that BlackBerry owners should spend less time talking on the phone compared to regular, to 18 to 24-year-olds using, different sort of cell phone or whatever. So if that's the case, our strategy is that we want to do our alternative hypothesis first, right? So this is a less than prediction. So the operator for our alternative prediction is going to be a less than sign. And then for our null hypothesis, well, it's simply going to be the opposite of that with an equal sign, right? For our null, it would be our sample mean should be greater than or equal to our population mean of 981, whereas our alternative is that our sample mean should be less than our population mean of 981. Let's do one more here, right? So in a sample t-test with a n equals 67, an alpha of 0.05, the t-critical of 1.34, and an obtained t-statistic of 1.57, which of these following is the correct presentation of the results? A, B, C, or D? Go ahead and pause the video, see if you can figure it out. All right. Well, first, let's start with what's supposed to go in the parentheses here, right? Remember, the parentheses is supposed to be our degrees of freedom. And our degrees of freedom is our sample size minus 1, so n minus 1. Our sample size is 67, so 67 minus 1 is going to give us a degrees of freedom of 66. And, looks like they're all 66, so it's all correct. So at this particular stage, we can't rule out either A, B, C, or D, right? At this point, any of them can be correct. Okay. Well, we know after we report T and our degrees of freedom, we need to report our obtained T statistics. So what was that? Our obtained T statistic was 1.57. Our critical was 1.34. So we know we're supposed to report our obtained statistic. So that's the case in A and B, but it looks like in C and D, we're reporting our T critical value, and that's incorrect, right? So that's good. We can rule out C and D. That means the correct answer has to be A or B. And then we're reporting our whether or not we reject or fail to reject, right? And that depends on the sign here. Well, if we look at our obtained T statistic, it's greater than our T critical statistic of 1.34, right? So if we were to plot that out on a normal distribution, if we wanted to create a visual, we would plot our T critical value as 1.34 and our obtained statistic is 1.57. So our obtained statistic falls in our critical region. So the correct answer there would be to reject the null hypothesis. So if we reject the null when we're reporting our p-value, the correct way to report that is p less than 0.05, right? Here's p greater than 0.05. That would be wrong. We would say p greater than 0.05 if we fail to reject the null. But in this case, the correct decision would be to reject the null, right? So therefore, the correct answer here in this particular scenario is A, right? T in parentheses 66 equals 1.57, p less than 0.05. Okay, now is the portion of the lecture where typically I would ask if there's any questions. In fact, if I recall correctly, typically when I deliver this lecture, typically class ends right before I did these little examples in blue, right? So, I probably should have mentioned that. But, again, you shouldn't watch this video all in one setting. Feel free to break it up into over 2 days, right? Because, this is again sort of an important chapter. We're still sort of getting comfortable, learning how to conduct hypothesis tests, right? We spent 3 class days doing this for one sample Z statistic, and the way this course is set up, it's designed for you to spend 2 days learning how to do a one sample t-test. So, if you feel comfortable with it, it's fine. Sit through, watch the whole thing, but also feel free to sort of break this up over 2 days in a way that's comfortable for you. Okay, so let's do one more example, right? One more example of a one sample t-test here, okay? And so we're going to be a little creative with this one here, right? So first, let me just give you this scenario. A standardized reading achievement test for 5th graders has a nationwide mean of 70. A teacher would like to know whether the students in her 5th grade class are significantly different from the national average. The test is given to a class of 25 students, and the average score was a mean of 75 with a sum of squares. That's interesting. A sum of squares of 2,400. What I want you to do is conduct the 6 steps of hypothesis testing at an alpha of 0.05, right? And then once you've done all 6 steps, I want you to sort of go back and find out whether or not you'd come to the same conclusions if our alpha would have been 0.01, okay? So you've got everything you need to complete the 6 steps here. Notice here that I'm not giving you the sample standard deviation, but I am giving you the sum of squares and the sample size. So if you remember what you learned in chapter 4, and this is important because we shouldn't forget how to compute things like variance and standard deviation of a sample, then you should remember how to do everything, right? So you might need to go back and peek at some notes for chapter 4, right, to sort of reacquaint yourself with how to compute the variance and the standard deviation when all you have is the sum of squares and sample size. But once you remember how to do that, you should be good to go. So go ahead and give it a shot. Do the 6 steps of hypothesis testing at an alpha of 0.05. And after you've done that, ask yourself if you come to the same conclusions if you had an alpha of 0.01. Pause the video, give it a shot, and when you come back, I'll go through these steps with you. Okay, so first we want to state the null and the alternative hypothesis. So hopefully you figured out that this is a two-tailed test, right? There's no directional prediction in this scenario. The teacher just wants to know whether or not the students in her class are significantly different than the national average. She's not making any prediction that her students will be better or her students will be worse. She's just asking whether or not her students are different, right? And so in that case, this is going to be a two-tailed test, right? And our operators should be equal and not equal for our null and our alternative hypothesis, respectively. So for our null hypothesis, we're saying, okay, the mean of our sample, right, the mean scores of our sample should be equal to the population mean of 70. And note, that was the national average, right? The nationwide mean was 70. So it should be pretty obvious to you that we're going to treat that data as our population data, right? So the mean equals 70 for the population mean. So our sample should be equal to our population mean, whereas alternatively, our sample mean of scores will be not equal to 70. It might be less, it might be more. We don't have a prediction sort of prior to actually doing the testing. So that's exactly what our hypothesis should look like in this particular situation. All right, now we want to find the critical value, right? So remember, we had a sample size of 25, right? We identified this as a two-tailed test, and our alpha was 0.05, right? So with that information, right, we should know, okay, well, our degrees of freedom is going to be 24 because n minus 1, 25 minus 1 equals 24. We're looking in the two-tail row at an alpha of 0.05, and our critical value in this case is 2.064. But be careful, right? This is a two-tailed test, so our critical value really is plus minus, right? Plus slash minus 2.06 if we round it to 2 decimal places. So we want to go ahead and plot these t-scores on a distribution, right? So on the left side it would be negative 2.06, and on the right side it would be positive 2.06. So when we compute the test statistic, if our results fall into either this critical area or this critical area, we would reject the null. But if our t-statistic is somewhere in between negative 2.06 or plus 2.06, we would fail to reject the null. Okay, great. But like I pointed out, you weren't given the sample standard deviation in this problem, right? You were given the sum of squares of 2400 and a sample size of 25. So what you need to do is compute the variance and then compute the sample standard deviation in order to find the sample standard deviation. And hopefully you recall those formulas or you were able to look them up in your notes. Remember, the equation for our variance is the sum of squares divided by n minus 1. So we have the sum of squares is 2400, and we're dividing that by n minus 1, so our sample size minus 1, or really our degrees of freedom, right? So we're dividing that by 24. That gives us a variance of 100. And in order to find the standard deviation, it's nothing more than the square root of our variance. So the square root of 100 equals 10, right? So in this case, our sample standard deviation is 10. So now that we know that, right, we can start computing the t-statistic. And the first thing we need to do is compute our estimated standard error of the mean. So we're going to use our sample standard deviation as a stand-in for our population standard deviation. So that's 10. And we're going to divide that by the square root of our sample size, which is 25. When we do that, we get an estimated standard error of the mean of 2. So that's what we're going to do. We're going to plug that into the denominator of our test statistic, right? And we need to figure out what the difference is between our sample mean and our hypothetical population mean. So our sample mean was 75. Remember, her students had a mean score of 75 on this particular exam. We subtract out of that the population standard mean of 70. And whatever that difference is, we're going to divide it by 2. And so when we do that, we get a t-statistic, right? A t obtained of plus 2.50. All right, so now we need to plot the results of that t-test. And when we do, it's going to be somewhere over here, right? It's going to be plus 2.50. And then the next question we ask ourselves is, well, does that fall into, since this is a two-tailed test, one of our two critical regions? And the answer is it does, right? It falls on the right side of our distribution, right? And it falls into the tail on the right side of our distribution. So since it does, we reject the null hypothesis, right? Our obtained statistic falls in a critical region, which means there's a significant difference between the performance of the teacher's class and the national average. So we reject the null. So since we reject the null, it's appropriate to compute the effect size here. And remember, it's a little bit of a different equation that we learned for the one sample z statistic. We're still going to take our sample mean and subtract out of that our hypothetical population mean, but we're going to divide that by our sample standard deviation. So when we do that, what we get is a Cohen's d of 0.50. And remember, we want to report the Cohen's d as an absolute value. We want to report it out to 2 decimal places. Well, there's nothing tricky we need to do here, right? It's already a positive value, and it's already reported out to 2 decimal places. So there's nothing else we need to do. Then finally, step 6, we need to write our results in APA format. And here's what I got. Hopefully you got something similar here, right? Obviously, the first statement should be we reject the null hypothesis. Then we want to report the results of our t-test. So remember, in parentheses here, after we write down t, we want to put our degrees of freedom, which was 24. We want to report the results of our t-statistic, which was 2.50. P less than 0.05, right? Because we rejected the null hypothesis and our alpha was 0.05. Because we rejected the null hypothesis, it's appropriate that we report the results of our effect size, right? Of our Cohen's d. So d equals 0.50. And then finally, we just want to say something about the direction of the difference. Well, at that point, we just compare the actual value of our sample mean, which is 75, compare that to the population mean, which is 70, right? So 75 is greater than 70. Our sample mean is greater than our hypothetical population mean. So we should say something to the effect that the students, right? And then we report the mean that should just be S. The mean and the standard deviation for our sample has significantly better test scores than the national average. There I report that mean and that the population mean for the scores for the national average. Okay, great. But remember, it also asked you to see if our results would still be the same. If our results would still be the same if we had a alpha of 0.01. Well, let's look that up then. Okay, so two tails, right? Still two tails. And we want to look in the column for 0.01. And we still want to look in the row for degrees of freedom of 24. So let's see what we get. Our t critical value would be plus minus 2.797. Well, our results wouldn't be significant in that event, would they? Because the results of our test statistic was positive 2.50. And that would not fall in the critical region, right? That would not be greater than 2.797. Really, we'd round that up to 2.80. That would actually fall in between our two t boundary values. So in that case, if we had set our alpha at a much more conservative level, right, at 0.01 instead of 0.05, in that instance, we would have failed to reject the null hypothesis. Okay, fantastic. Let's have you do one more final example, right? This is not too terribly complicated, but I do EEG in my laboratory at my university. So I like to include a little neuroimaging example from time to time, since you're all psychology majors. So the results from a meta-analysis, a meta-analysis is a type of paper that looks at the statistical results of a bunch of similar experiments and sort of does reports some additional statistics on all these different findings. But anyway, the results from a meta-analysis show that EEG data in response to imitative stimuli, right? These are watching videos and imitating people's actions. It generates mean mu-band activity of 2.37. So mu-band activity is just a way of us in the EEG literature, a way for us to say brain activity. It's just a fancy way of saying brain activity. So the results of this meta-analysis in response to imitative stimuli show a mean activity of 2.37. I want to know if the data that I collected in my lab is different from what's been reported in the literature. So I ran 30 subjects. I got a mean of 2.23 with a standard deviation of 0.32. I want you to conduct a hypothesis test as to whether or not these values are different using an alpha of 0.05. So go ahead and pause the video, run through the 6 steps of hypothesis testing in this scenario, and when you come back, I'll show you what I got. All right. First things first, state the null and the alternative hypothesis. So hopefully you figured out that this is a two-tailed test here, right? Because I'm not making any directional predictions. What I'm saying here is I want to know if my data is different from what is reported in the literature. I'm not making any prediction about my data being less or greater. I just want to know if it's different. So therefore, it's a two-tailed test. So this is exactly how you should state the null and the alternative, right? The null would be that my sample mean should equal my population mean. So I'm using the results, the data from the meta-analysis here is my population data. So my sample mean should equal 2.37, or alternatively, my sample mean should not be equal to 2.37. Maybe my sample will be less, maybe my sample will be more, but I didn't make any directional prediction. So now we can move to step 2, right? We want to find the critical value. So my sample size was 30. I've got an alpha of 0.05, and we've already established that this is a two-tailed test, right? A two-tailed test. So the first thing we need to do is figure out the degrees of freedom. So the degrees of freedom, again, is n minus 1. So 30 minus 1 is going to give us a degrees of freedom of 29. We've established this as a two-tailed test and an alpha of 0.05. So if we go down this column, right, and find the degrees of freedom of 29, we get a t critical value of 2.045, of which we can go ahead and round up to 2.05. But don't forget, this is a two-tailed test, so really it's plus/minus 2.05. Now, once we've found the critical values, we want to go ahead and label them, right? Label them on our distribution. And this is roughly what it should look like, right? Negative 2.5 is going to be on the left side, somewhere just right after negative 2 standard deviations. And positive 2.5 is going to go on the right side of the distribution, somewhere after, right immediately after sort of 2 standard deviations above the mean. And again, once we run our statistic, if the results of our statistic fall into this critical region, one of these 2 critical regions, we would reject the null. Otherwise, if it falls between these 2 values, we would fail to reject the null hypothesis, right? So again, let's run our test statistic. The first thing you should have done is compute the estimated standard error of the mean by taking your sample standard deviation and dividing that by the square root of your sample size. When you do that, you get an estimated standard error of the mean of 0.058. So that's the value we're going to insert in the denominator of our t-statistic. We've already got that figured out. But now we need to take our sample mean and subtract out of that our hypothetical population mean. So we're going to go 2.23, which is our sample mean, minus 2.37, which is our population mean. We're going to divide that by our estimated standard error of the mean. And when we do that, we get an output for our test statistic of negative 2.41. So you should have went back and plotted that, right? Plot the results of your t-test on your distribution. And when you do, negative 2.41 is going to be somewhere over here. And so you ask yourself, well, does that fall in one of my 2 critical regions? And the answer is that yes, indeed, it does. So our decision in this case should be to reject the null hypothesis. Now, since we rejected the null, it would be appropriate to do step 5, which is to compute the effect size. And again, that's nothing more than computing Cohen's d, right? Taking the sample mean, subtracting the hypothetical population mean, and dividing that deviation by your sample standard deviation. And so when we do that, we get a Cohen's d of negative 0.4375. But remember, round that to 2 decimal places and report that as an absolute value. So your Cohen's d should be 0.44, right? So you get a medium effect, right? A moderate effect, but a fairly robust effect size for psychology. Then the final thing you need to do is just simply write up your results in APA format, of which there are 3 sub-steps that belong underneath this final step 6. The first thing you want to say is we reject the null hypothesis. And then you report the results of your t-statistic. So t, and in parentheses, your degrees of freedom of 29, equals the results of your t-statistic, right, which is negative 2.41. We're going to say p less than 0.05, right, because we've rejected the null hypothesis, and we set our alpha at 0.05. So whenever you reject the null, it's always p less than whatever your alpha is. Then it's also appropriate to report Cohen's d here, right, because this is going to drive me crazy. That needs to be italics. Okay. You're going to report the results of your Cohen's d, which equaled 0.44. And that's all you need to report, right? The t, degrees of freedom, the obtained statistic, p less than whatever your alpha, and if you reject the null, then report the results of your effect size test, which in this case is a Cohen's d. And then we have to write some sort of statement, right? Some sort of statement about how our sample mean differed from our hypothetical population mean. So, I've written here, participants' response to imitative stimuli in my lab. And note, I report the mean and the sample standard deviation was significantly lower than the population mean. Boy, I got all these little annoying little things there. At least I can correct them. This is what it should look like, right? Mean, standard deviation. It was significantly lower than the population mean. So that's all the required little sub-steps under step 6 in order to appropriately write up your results in APA. Okay, so that's it. That's all we've got for this. There are some questions from the back of the chapter. if you find you need a little bit more practice. And note that for questions 15 and 17, it looks like 15B and 17B, those are questions that relate to confidence intervals. And remember, I'm going to lecture about those after we get through all the t-test lectures, right? So I'll have one recorded lecture that teaches you how to compute a confidence interval for a one sample, independent sample, and related samples t-test. So don't worry about doing 15B and 17B, but you should be able to do everything else if you find that you need any practice. And remember, we're in a 2-day lecture for this chapter here, right? So don't feel the need to rush this. You've got 2 days to get through reading the chapter. You've got 2 days to get through. Well, actually, you should have read the entire chapter before you watch this video, if you're keeping up on the readings. But you've got 2 days to get through the video and do the practice problems and do the things you can do on the homework. So again, it's a marathon. It's not a sprint, right? So it's more important that you make sure that you understand the material rather than just simply go fast. Okay. So that's it. I'm done for this lecture. So if you have any questions, just let me know.